Hi. So in the previous video, we did a few examples about ordinary points and how to determine ordinary points and singular points of a given differential equation. So we continue by stating the following theorem about the existence of power series solutions without proof. So this theorem states that if x equals x sub 0 is an ordinary point of the differential equation 1, and if you remember this differential equation 1, we mean this differential equation a sub 2 of x, here we have y double prime plus a sub 1 of x, y prime plus a sub 0 of x, here we have y is equal to 0. That was our equation. Talk about this second order linear differential equation. And here it's saying that if x sub 0 is an ordinary point, that means that here a sub 2 of x sub 0 is not equal to 0, right? Then we can always find two linearly independent solutions in the form of a power series centered at x sub 0. That is the solution. The first solution is this: y is equal to n equals 0 to positive infinity c sub n times x minus x sub 0 to the power n. And in similar way, we can find another solution so that the linear combinations of this y sub 1 and y sub 2, it gives us the general power series solutions of the given differential equation. A power series solution converges at least on some interval defined by absolute value of x minus x sub 0 less than capital R, where capital R is the distance from x sub 0 to the closest singular point. And a solution of the form y equals this thing is said to be a solution about the ordinary point x sub 0. So the distance R in this theorem is the minimum value or lower bound for the radius of convergence. Now we will consider one example about this theorem. Minimum radius of convergence. Find a minimum radius of convergence of a power series solution of the second order differential equation. It is given by this: x squared minus 2x plus 5 y double prime plus x times y prime minus y is equal to 0. Part A, about the ordinary point x equals 0, and part B, about the ordinary point x equals -1. So let's start with part A. As you see here, the leading coefficient that a sub 2 of x, that's equal to x squared minus 2x plus 5, right? Now by the quadratic formula, we can find where actually this equation is equal to 0. So that is equal to 0. So discriminant is equal to b squared minus 4ac, that is 4 minus 4 times 5, which is equal to -16, right? So the first root of this quadratic equation is, it is 2 plus square root of minus 16 over 2, which is equal to, here we have 1, square root of 16 is 4, it is plus 4i, right? Actually, we divided by 2, right? Here we have 1, here we have 4 divided by 2, so it should be 2 here. Then also we know that always if the roots of the quadratic equations are complex, the roots are conjugates of each other, right? The second root would be 1 minus 2i, right? Because x equals 0 is an ordinary point of the differential equation, and our previous theorem guarantees that we can find two power series solutions centered at 0. That is, we can find two power series solutions, right? The first one is, let's say y sub 1 will be sigma. Here we have n equals 0 to positive infinity. Let's say here we have c sub n centered at 0. So here we have x minus x sub 0, which is equal to x minus 0 centered at 0, right? That's equal to x. So here we have x to the power n. And also we know that we can find the second power series solution that will be also centered at 0, n equals 0 to positive infinity. Let's say here we have d sub 1 times x to the power n, right? Then actually we can find the solution of this differential equation as y equals c1 times y1 plus c2 times y2. Okay, so actually in this question we are trying to answer this question, right? We need to find the minimum radius of convergence of a power series. So to do this one, since these 2 points are singular points, right? The theorem says that the r is the minimum distance, right? From the center of, actually this, what is it, about the ordinary point from 0 to the closest singular point. So if you just plot this, here we have xy plane, right? And 1 plus 2i. Let's say this one is 1, and here we have 1, 2, here we have 1, 2, and here we have the first point, and here we have the second point, right? So this point is, what is it? 1, 2. That is this point in complex plane. Second one is this, that is 1, negative 2, right? So if you find the distance, what is the closest distance? That is our r, that is r, the closest distance. From here, r is equal to square root of 1 squared plus 2 squared, 1 squared plus 2 squared, that is equal to square root of 5, right? So that means that each series must converge at least for these values, right? Because here that radius of convergence is square root of 5, right? So that means that on the number line, okay, the series, if you just pick centered at 0, that is minus square root of 5, and here we have square root of 5, right? If you just pick any point from this interval, right, actually these two series will converge, okay? That's it. How about part B? It says that find the minimum radius of convergence of a power series, solution of the second order differential equation about the ordinary point x equals negative 1. So we will continue here. X equals negative 1 is an ordinary point of the differential equation. Let me rewrite our differential equation here. That is, we're talking about this differential equation, x squared minus 2x plus 5. And here we have y double prime plus xy prime, and minus y is equal to 0. And singular points are, what are these? 1 plus 2i and 1 minus 2i. So singular points, right? 1 plus 2i and 1 minus 2i. So in our question, it's saying that about the ordinary point x equals negative 1. So here we have, again, if I draw our xy plane, right? And that is 2 points. This one is 1 plus 2i, that is 1 and 2. This point is 1 and negative 2, right? And here we have negative 1, right? So to find the radius of convergence, right, it's in the theorem it states that the minimum distance from this point to the closest, to the closest singular point. So we are talking about this. Or since they are symmetric, or this doesn't matter, right? So from here, then what is r? The radius of convergence is equal to, here we have 2 points, right? The first point is negative 1, 0, to which point? It is 1 and 2, or 1 and negative, doesn't matter. This distance are equal. So here we have negative 1 minus 1. So here we have negative 1 minus 1 squared plus 0 minus 2, 0 minus 2 squared, just using distance formula, right, between 2 points in the xy plane. Here we have negative 2 squared, 4, 2 squared equals 4. So here we have square root of 8, or 2 times square root of 2, right? That is the radius of convergence of the power series solutions of this differential equation. So that means that here we have x minus x sub 0, right? And this gives us the interval of convergence. What is our x sub 0 here? X sub 0 is -1. So here we have x sub 0 equals to -1. So x minus -1, which is equal to x plus 1, that is less than 2 square root of 2, right? So also we can find the interval of convergence here. For this question, radius of convergence is 2 times square root of 2. And this gives us, if we draw a number line here, right? Here we have -1, right? And here we have 2 square root of 2 minus 1 plus 1. It is plus 1. And here we have minus 2 square root of 2 minus 1. Right? Because this thing is, since if we solve this inequality, here we have minus 2 square root of 2 less than x plus 2 less than 2 square root of 2, right? By just adding, subtracting 1, sorry, here we need to subtract 1. We need to subtract 1, right? So at the center of this interval is the interval of convergence, right? If you pick any number here and substitute the power series solutions of this, it will be convergence. And what are those solutions? It looks like something like this, right? Y is equal to, here we have sigma notation, n equals 0 to positive infinity. Here we have c sub n times x plus 1 to the power n. All right.